Thank you very much. Right, thank you very much for the introduction, Chase, and thanks to the NeurIPS organizers for having me here.
Trying to get rid of the thing.
Yeah, no, it really is an honor. Like we've been part of the. Okay, can we? Yeah. Let's try to.
Sorry. I lost my. Oh, there it is. Perfect.
Okay. Cool. Almost there.
Technical difficulties.
All right. So actually, let me just start straight off. First of all, apologies that David's name is not listed on the title slide. This was a talk that I gave a couple of days ago, which also contains some CV or resume elements. So sorry about that. But this painting actually is very dear to me, and also it follows actually from my engagement with the NeurIPS community, because Christian Shoemake, one of the organizers behind this, actually brought this painting to my attention when we were talking about inference models and how we tend to focus so much on geometry. And we'll get back to this painting in a minute. But what I want to start off with is the state of the art in generation. So this is video generation. Well, it's not really state of the art anymore because it's from February 2024. But basically, this is to exemplify where we are somewhat, right? This is a video of a glass of lemonade falling and shattering. And you see some of these prompts nicely correlate what we see in the image and the other way around. We see broken glass and we see spilled lemonade, but the physics and the geometry of all is pretty messed up and inaccurate. And it's the same with this kind of video where we see nice puppies playing on a gravel road. But if you look carefully, you see them merge into each other and magically merge out of each other. So this is crazy if you look carefully at it. And yeah, I think this is a really big limitation of the current deep learning field as such. We see that even the biggest foundation models, the biggest models still struggle with representing physics and geometry. And these are the biggest models, and the prevalent opinion in the field still is that of scale is all you need. And while I do believe that scale is incredibly important for success, I don't believe it will solve these problems. I think we will always run into issues like these. And so from my point of view, I think the scaling argument is not only naive because of data availability reasons in many domains of interest, we just don't have the sheer amount of data, but also considering surrounding ethical issues and environmental impact problems. In summary, my response to this is geometry is all you need. Obviously, this is a very much compressed summary, but I'll get back to this throughout this talk. Now, I show these videos because it basically shows that even these biggest models struggle with basic concepts from geometry and physics that underlie our physical world or our reality. And it's an eye-opener because it shows that not only these models struggle with these problems, also, in my view, any other AI system trained in such a way is in that way inherently unreliable. For example, if you train a medical image diagnosing model to classify cells and you rotate the cell, we actually see that quite often it will predict the exact opposite thing, right? And in these kind of safety critical areas, in medical settings, these kind of mistakes are really intolerable. And my experience and my view on this is that scale won't fix this. I've seen this over and over again in my application in medical imaging. So the solution to this, and that's what I started when I started my career at the UVA with the grant, was to build a geometric structure into neural networks such that, well, if this cell were to be rotated, then the machine learning model would still classify the cell as the same type, because it's inherently structured to respect the symmetry structure. So this is known as the group convolutional paradigm, and it leads to provable robustness and well, due to the principle of equivariance. Okay, now it's gonna get a bit awkward. I'm getting back to my CV part. So what you're gonna see next is the most amount of self-citations in a minute. So let me rush over this. But this is just to sketch my career path. Like, how did I get to this point? So, as Chase said, I did my PhD in Eindhoven on sub-Riemannian geometry in SE2, and this for me gave me a good foundation to geometry. And from there on, I started a postdoc on this grant, which I just showed, basically that followed from this, working on the first group convolutional neural networks in medical imaging domains. And from then on, I just focused on expanding this paradigm, just figuring out what are theoretically the possibilities, but also practically what are the useful tools to do this. So going from regular group convolutions to steerable group convolutions and tying them together. And this eventually led to, well, this course, group equivariant deep learning, for which I recorded videos. So if you're interested in this, just Google on YouTube on group equivariant deep learning, and you find a lot of resources on this equivariance paradigm. And since then, I've been increasing my involvement also on the European level on the ALICE program on geometric deep learning. And what I want to highlight actually is this particular paper, because for me this also was a motivating example to sort of really take a critical look at the scale is all you need argument. Together with Artem Moskalev, we looked at the role of data augmentation to obtain geometric properties. And basically what we figured out that this data augmentation only leads to what you could call apparent attainment of invariance or equivariance, right? And so it seems that the model is invariant, but as soon as there's some sort of domain shift, like the pixel intensities change because of the camera calibration fails or whatever, then you lose these kind of these properties. And to me, this shows that only through hardwiring the structure in the data or enforcing the structure in other ways, you can actually get reliable models. Data augmentation and scale alone will not solve this. Okay, and since then I've been moving a bit more towards the generative modeling paradigm of geometric structures, and lately expanding more into the equivariant neural fields. And this is a principle that David Knigge will expand on in more detail, but we try to approach it from a representation learning perspective. And I think it will solve some fundamental problems eventually. And this is what I recently got a grant for to expand on for the next 5 years, to go into inference models of what I would call geometry-grounded representation. So the idea is that you have an image, and we build up a representation that the neural network can compute with, and this representation is inherently geometric, and it's grounded in the input space because it satisfies certain equivariance properties. So we'll get back to that in a minute. And it's loosely inspired by models of perception based on posterior inference. So far I've been primarily focusing on building out this paradigm of equivariant deep learning. Obviously I'm not the only one, but this was just a sketch of how I went into this field. So after this, you might think that my approach to solving these kind of problems with misrepresenting physics and geometry is group convolution is all you need. And this is something that I quite often talk in my lectures, but I do not think actually it's the full solution. And I want to highlight where we currently stand. So this group equivariance paradigm brought us a lot. For example, we have reliability. So with molecular energy prediction, which is supposed to be invariant, right? We can actually make architectures that are invariant by design, and we gain a lot of data efficiency too by that. Equivariance is an example where you predict force vectors and they rotate accordingly with the input, so we can guarantee these kind of properties. Same with cell detection or the kind of medical data. This is actually where these symmetries are exact, right? We have an in-plane rotation of a tissue under a scanner, and the image rotates accordingly, and we can handle these symmetries exactly. But even though we have all these advantages, the framework is inherently limited because of scalability issues. So now we look at somewhat basic symmetries like translations, rotations, maybe scale adding to it. But if we go to more advanced symmetries, basically the simple group convolution paradigm doesn't scale so well. It scales approximately with the size of the group. So if you're interested in larger groups, you need, well, significantly larger computational resources. But actually what I want to argue is that the source of the main scalability bottleneck is actually that of implicit versus explicit access to geometry. What we've seen is, for example, with point clouds, we have explicit access to coordinates, and we can explicitly talk about distances between points, and we see that this is actually the region where equivariance and geometric processing really shines. But if you look at the image data, the geometry is intrinsic. It's hidden behind the pixels, if you will, right? Even though these pixels are the shapes that you observe are really essential in determining what you're looking at. And so this really brings me to the fundamental problem of many issues currently in the deep learning paradigm, and that is really that the essence of a concept is often geometric. For example, in this painting for terminus, you'll see that, well, you easily observe the notion of a face of a person in this, right? Even though there's not a real person there, it's just a configuration of fruits and vegetables relative to each other. So it tells us that our perception and our notion of, well, reality heavily relies on a notion of geometry. But in the eyes, if you will, of an AI system, we see nothing else as a bunch of pixels, right? And basically this geometric structure is not reliably representable by current AI systems. This is known as the texture bias in current AI systems. And basically our current research focuses on addressing this fundamental limitations. So if you look at where does this texture bias come from, this is a simple example of two smiley faces which are really close to each other, right, perceptually. But if you look at the overlap in pixel space, there's barely any overlap there, right? And so they're close in concept, but they're large in distance in pixel space. And this also explains why these videos of these puppies playing on the road, they look kind of natural, and maybe if you just look at it at a glance, you would say, okay, nice scene, but if you look carefully, then it doesn't make sense at all. And it is because these models are optimized on, well, pixel distances, on textural patterns and such. Yeah, so my solution to this would be to focus on inference of explicitly geometric representations of data. And in that case, for example, you see the blue and the light blue dotted dots, they would still be close in a geometric distance. Yeah, and that would tell them close together in representation space. And that's the purpose of this grant, which I'm going to work on for the next 5 years, called SIGN. It's the project Scalable Inference of Geometry-Grounded Representation Learning. And the essence of this is really the notion of a conditional neural field. This is a way to connect geometric representations with actual images, with field data. And that's something that David is going to explain in a minute. But in this comes together like these kind of notions, the notion of equivariance that says, okay, this representation corresponds to the actual image in a geometrically sensible way. Notions of generative modeling come in because now we can talk about shape spaces and statistical shape models based on representation models or generative models in this geometric space. Bayesian inference comes into the encoding pipeline, and also the generation part, also basically the readout of these equivariant neural fields. So my point of view, we're so far have been primarily focusing on equivariance as an engineering tool, and we figured out a lot of different methods to make sure that our convolutional neural networks or point cloud methods satisfy certain equivariance constraints. So we have a lot of tools available for that now. And I feel now we're entering a new phase where we start to discover, okay, what can we do with these tools other than just considering equivariance as a constraint? For me, equivariance is more a way that enables building richer representations to be able to reason in terms of geometry. So that's why I hope to see that, well, we're now entering a second wave of geometric deep learning, which I would refer to as geometry-grounded representation learning. Yeah, so with that said, I would like to give the word to David to go over this idea of geometry-grounded representation learning.
Thank you. All right, thanks. Yeah, so I'll be giving you a quick intro on this project on equivariant neural fields that I've been working on together with Erik for, I think, yeah, someone just said it's the past year now, so it's been quite a while coming, but we're finally getting some very good results, so very happy. So yeah, the ultimate goal is to find a geometry-grounded representation of data. Before we get there though, earlier today I heard someone call this whole notion of learning over primary spaces esoteric, so it's a bit out there. So I'll just give a quick intro on what this actually means, what functa as a concept is. So we're discussing this paper. It's a collaboration between a bunch of people here at UVA. So the concept of neural fields, very simply, is to fit a neural network to a field. So what is a field? In this line of work, a field is interpreted as any signal that can be defined over a coordinate space. So as long as you have basically coordinate signal value pairs, that's a field. So A simple example, come back to a lot, is an image. The image is, of course, you can see it as a discrete function over pixels, so pixel coordinates mapping to pixel values, right? This is then a discrete function, and the goal of a neural field is to learn to represent this image implicitly with a neural network. The intuition there is that this image is actually sampled. It's a discretization of a real world, like a continuous thing, right? As soon as you're taking an image, you're sort of discretizing, let's say, the real world. And yeah, neural fields are just a way of trying to approximate the underlying continuous function that actually generated this image. And it's quite simple. The idea is that you have an MLP or a specific type of neural network that takes in coordinates and it spits out the signal value. So in the case of an image, this would be a simple neural network that takes in XY pixel coordinates and then spits out RGB values. And now you can fit one of these networks to each of the samples in your data set. And the main concept is then that these sets of parameters each individually now encode information about the image, right? Because this network is able to represent or reconstruct the whole image, it must mean that all this information is stored in there somewhere, right? And yeah, so the main concept here is that you can then use these sets of parameters to actually learn over. So you can use them as a representation for downstream tasks. So for example, classification could now be done instead of on pixel space, you could do it on the parameters of these neural fields. And there's a couple reasons why you might want to do this. These representations, of course, are resolution free. So it means that they're not tied to any grid. You can sample any coordinate you like after you fit these neural fields. So it's not necessarily restricted to pixel grids. They are data type agnostic, meaning you can fit them to any data type as long as you have coordinate signal pairs. So they also work quite well for 3D data, for shape data, videos, stuff like that. And another quite nice thing, I think, is that there's been ablation studies that show that the size of the networks that you need to represent signals doesn't actually scale with the resolution, for example, in the case of images. Instead, it scales more with a notion of signal complexity. So let's say simpler image data sets can be represented by simpler neural networks. So that's actually quite a nice, quite a nice property intuitively to have. Representation actually scales with complexity instead of discretization resolution, for example. So methods that operate directly on these sets of parameters are called weight space methods. And the idea is just that you now use these parameters as input to another neural network, and this other neural network has to learn to, for example, map these parameters to class labels. So in the field of weight space methods, you can, of course, apply these types of methods not only to neural fields, but also to a whole host of other kinds of neural networks, any architecture actually. And the thing is that operating on these weight spaces is actually quite complex. So there's a lot of symmetries that are inherently present in neural networks. So you can, for example, permute rows and columns of adjacent weight matrices, you get the same output. There's a bunch of scaling symmetries and stuff like that. And another big thing in the case of neural fields is that very perceptually similar looking functions might be parameterized by completely different sets of parameters. So it makes it quite hard to operate on these parameters directly. And so it means that the performance of these methods is quite limited until now. So for example, these are classification tasks. Cipher 10, the test set accuracy lies somewhere between, let's say, 45 and 65% usually for these methods. That's not great considering you can do much better with just a CNN on pixel space, right? And so in comes the idea of conditional neural fields. Essentially what the idea behind conditional neural fields is that usually in a data set, for example, data set of images, there's going to be a lot of similarities between images. Right? There's going to be a lot of repeating patterns and texture that occurs in image A, but also in image B. And so intuitively, it might also be a bit redundant to learn to optimize networks for each of these signals separately. There's actually a lot of structure shared between all of these samples. The idea behind conditional neural fields then is to share the neural field itself, so share the parameters data over the entire data set, and instead only learn what's known as a latent or conditioning variable for each individual sample. This conditioning variable then, for example, it gets multiplied by the activations, or the activations get shifted by this conditioning variable to get sample-specific outputs. That's the main idea. And you can then optimize the network weights data and the latents both using gradient descent. And then fitting a data set is no longer fitting a set of parameters to each sample, it's only fitting a single latent vector, which becomes a lot more manageable. So you share the backbone, the data parameters of the neural field over the entire data set, and instead you fit this single latent to a specific data sample. And now you can use this latent in any downstream task you like, and this is mainly the idea behind functa. So this notion of learning over functa is essentially this. And it does a lot better than weight-space methods. So they show a bunch of nice results on generative modeling, in painting, and well, they also show that you can do this on for example, point cloud or voxel data, weird geometries. However, all of these data sets are globally aligned, and performance on more realistic natural data is still kind of disappointing. So we now get to 68% test set accuracy in cipher classification, but it's still not great. And trying to do generative modeling over these latents also clearly doesn't work. So our hypothesis on what is missing in these methods is exactly this notion of geometric latent space. For example, if you rotate your image slightly, you end up with the rotated image, of course. There's no real clear notion of what this would do to the latent, right? This latent encodes sort of this global function, and there's no real interpretable way that you can now operate on this latent to end up with a latent that encodes for the rotated image, for example. And then the second thing that we think is really important is this notion of locality, and it's basically that a very small perturbation to a part of the image is going to result in changes to all of the coefficients of your latent vector, right? And vice versa. So any small perturbation to your latent vector also has an effect over the entire output of the neural field. And the idea for this work on equivariant neural fields is then to find a latent representation for neural fields that does have explicit geometry and that does have this notion of locality. And we do that essentially by replacing this single latent vector Z by a point cloud of localized latent vectors. And right here's an illustration. So the idea is you now have a bunch of smaller latents that each have an associated pose, which could, for example, be a position, or maybe a position and an orientation, as is the case in this image. And these latents are localized in the field itself. So it means that this latent at the top left, for example, we would like to have it encode for the top left ear of the cat. So that's the main idea behind equivariant neural fields. And then you can fit these new latent point clouds to data samples and use them as surrogates for your original data. The nice thing about this parameterization is that it also comes with a very clear notion of geometric transformations in the latent space. So you can now, as I was saying earlier, if you rotate your image, what do you do to your latent space? In this case, now you have a point cloud with where the latents have their own position and also the orientation. You can actually act on the output of the neural field by acting on the latent set. So this is the what we call the steerability property of equivariant neural fields, and essentially it just says that a transformation to the domain of your neural field, so you can either rotate the pixel coordinates that you put into the neural field, can also be achieved by applying a transformation to the latent set itself. And yeah, this makes the whole thing equivariant, essentially. Now, a bit more detail then on how we make this happen. At the core is really this steerability property, and yeah, we can show that this steerability property of equivariant neural fields has an effect on the type of function that we can use to parameterize it. Essentially, it says that the steerability imposes this notion of bi-invariance. Essentially just says that if we want the steerability property, we should have a function that is what we call bi-invariant to group transformations, meaning that if we act on both the input coordinates and the latents in the same or opposing ways actually, then the output of this network should be identical. And from this it follows that any function that has this property has the properties that we want essentially. It has this notion of steerability, and so that's what we're looking for. And I won't go into detail on these bi-invariants that much more, but essentially it is an implementation of work that Erik did earlier, and he's also going to talk about a bit more later. So for the specific parameterization of this function, we look towards transformers, which makes sense because our latents are now a point cloud, so it's a set with positional information. So then transformers are a natural choice, we think. So how does this work? How would we encode an image, or actually decode an image with this data set? So this is a very beautiful image of a flower. Let's assume for a second that we have a set of latents that encodes for this flower, and we're going to look at, so each of these dots is a latent and has an associated latent vector. We're going to look to decode a specific coordinate in the image. The first step is calculating these bi-invariant properties. Essentially, these are exactly the properties that I discussed earlier. These are a function of the two inputs, so of the coordinate and the latent position, that are bi-invariant to these transformations. So you calculate these. Essentially, you could just think of this as the relative position, for example, of an input coordinate to a latent. That's the first step. This is an implementation of this notion of a geometric bi-invariant attribute that Erik will discuss a bit later. So you calculate this bi-invariant, and then the next step is to use this bi-invariant as a query in a very normal attention operation, essentially. So input to the query function is this bi-invariant, so just the relative position from a coordinate to a latent. Input to the key function is simply the latent vector itself, and then you would calculate the potential coefficient for a single coordinate for every corresponding latent in the latent set. And essentially how I like to think of this is as it's just a way of assessing how much a latent attribute or contributes to the output at a specific coordinate location. If that makes sense. So that's what you calculate with this attention coefficient, and then, like we do in a normal attention operation, use these attention coefficients to weigh the value vectors, and these are simply functions of the latent vector itself and then the relative position again to the latent vector. So this is really what exactly does this latent then contribute to the specific signal value at this location. Does that make sense? Is that clear? This is sort of the main contribution of this work, the main technical takeaway.
I can ask a question.
Of course.
So if I understand correctly, so basically it boils down to have a coarse representation. So you basically have a coarse-grained representation of your domain, and then you structure your latent space basically to have a color channels, what you call C or whatever, and then positions.
Yeah, so it's not necessarily colored channels. It is more like a high dimension. Yeah, so it's more of a high-dimensional representation usually. But I think that is a good way to think about it. Yeah, so you're really looking for a sparse, I guess, representation of your input signal, and then the main property that we would like this to have, it must be a neural field, so it has to be continuous in the output space, and for that we use this very specific attention operation. Yeah.
Right. If I'm allowed to elaborate.
Of course.
So how do you select the positions of those coarse-grained points?
That's a good question. In practice, we optimize them. I'll get to that a little bit later. But this basically comes down to the question, how do you obtain your latents, right? So how do you know at which location you would like a latent and what value must this latent have? So we're going to get that in a second and see there's another question.
So in this picture of these cats, you also show that each latent representation has a pose.
Yes.
So it has the coordinates and then it has a direction.
Exactly.
So how should I understand these directions in the latent? So I understand how they transform, but how should I see them? Why are there directions?
Why are there directions? So this is essentially a choice of exactly what transformations would you like to be equivariant to. And turns out that if you want your latent set to be able to rotate like this, you need to have some notion of orientation also in your latent space, right? And so these orientations, you could really think of them as, really the orientation of this sort of latent feature. So the orientation of, for example, the ear is what we would like to encode.
Can I elaborate on that? So I like to think of these images being composed of local patches. And each patch is centered around a pose, a position. And now, using this attention mechanism, we stitch all these patches together in a nice and smooth way. If now this point cloud needs to be a space on which the group acts, so it could be just a 2D coordinate, so I can translate a coordinate. It could also be a group element itself, so essentially these are the elements of SE2 of the rotor translation group. And you can think of this arrow as I'm going to stitch a patch over here under this orientation, or I'm going to stitch it over there under that orientation. So now we have orientation information. If this point cloud would only be a positional thing, and I want the entire neural field to be rotor translation equivariant, then I can only leverage pairwise distance information. Then I can only tell what is the pixel value relative to this one. I can only assume it based on the distance to that point. So I can only stitch isotropic patches together. But now I have orientation information, I relax that constraint, and I can pitch fully non-isotropic, like merely an ear at that location. If I only want to be translation equivariant, then I can really leverage relative position information, so delta x, delta y, to sort of represent my patch, the value function, essentially. Yeah.
It's because in this example, they all rotate when the whole image rotates.
Yes.
Technically, you would expect that the cat maybe hears us or hears something in the back, and only the ear will change, and then only the rotation of that specific latent should change, and not all do it the rest.
Yeah, so, hopefully that happens.
David will talk about PDE forecasting, where we're actually going to dynamically change these latence representation over time, and then you really leverage this notion of locality, that only the ear changes, for example, or some pattern.
So there's a question online, what if you have reflection as a group action? How could you incorporate that? You could also save this for afterwards.
I'm going to save it for afterwards because I don't have an answer ready right now. Okay. So let me think on it a little bit.
I had a question on the premise.
Yes.
What makes this approach better than just doing an equivariant encoder type of architecture?
I can answer that. I like to answer that because we worked on that in the past, like these equivariant encoders. We know how to do rotation equivariance and rotation invariance. But this is very surprising when it comes to encoders. Translation equivariance doesn't make sense, because if you look at an encoder, you gradually downsample an image, until you get one vector out of it, but you made it invariant to translations, because that was part of the sparsification procedure, this pooling. And so now if you have one image of a cat and a shifted image of a cat, ideally they should be mapped to one and the same vector, but then you're no longer able to decode it to the right position, right? So surprisingly, well, it's kind of makes sense, but surprisingly the problem of translation equivariant is not solved at all when it comes to compressed representation learning. And in this case, we have a way of connecting these point clouds to a full image, and we can make a translation equivariant. And this is a main thing. So we worked on rotation, invariant, and equivariant autoencoders, like Shafi worked on Kendall shape space representations. So that solved the problems of rotation invariance and equivariance, but not translation equivariance. And so that's why we opted for this approach.
Couldn't have said it better myself.
I'm very passionate about this.
Okay, I'll move on because I see I'm also running out of time. So main takeaway here is that we use this attention operation based on, for example, relative positions between the latents and the input coordinates. So as you might have noticed, this doesn't directly give us locality, which is one of the other desirable properties that we wanted, right? And so this is what we actually observed in our initial experiments. If we just use the 3 steps that I denoted here, then we actually end up with latents that still activate over the entire image, and so they don't activate for local patches at all. They just learn some sort of high, some sort of like frequency decomposition of the image, let's say. So in practice, what we do is we do a soft constraint on the attention operation. Essentially, we just weigh the attention coefficients with a Gaussian mask, which depends on the absolute distance from the latent to the input pixel. So the note on the right here. The idea being that pixels closer to a latent have a higher attention coefficient for this latent. So that's what we actually use in our experiments as well. So how do we obtain the latents and their positions is the question. So what you usually do with neural fields is you use auto-decoding or meta-learning to obtain your parameters, and essentially what it means is just using gradient descent to obtain them. So you usually initialize them either randomly or to a fixed value, and we found that initializing them somewhat uniformly over the domain of your data gets the best performance. So in practice we do that. You then decode these latents into your image. You end up with an MSE loss, and this loss, you take the gradient with respect to the latents and you update the latents accordingly. And you do this a couple times, and you end up with latents that have successfully learned to represent the image. And then in practice, what we use is it's called meta-learning, and that just means that to then obtain the weights of the neural field itself, we backpropagate through these 3 steps of gradient descent back to the original neural field parameters. And this then, essentially, you're optimizing for a neural field that is able to fit signals within 3 gradient descent steps. This is how you should think of it. And this is then the amount of steps that we actually need to fit an image is 3 gradient descent steps, so that's doable, I would say. And yes, and then you end up with this grounded latent, where the latents now have a pose and a corresponding context vector. So very quickly then, to summarize, using equivariant neural fields as a representation, first you need to obtain the latents, so you fit them to an image using meta-learning, and then you can use this latent set for any downstream tasks you would like. So for example, segmentation classification, or this notion of transforming your function, for example. Then we're going to move on to some experimental results to show that this actually works a little bit. What we're showing here is the output for neural fields where we transform the latents with different bi-invariants. So the bi-invariant is this thing that we had earlier. So the sort of the geometric bi-invariant attribute between the latent and the input coordinate that determines exactly what equivariances your equivariant neural field has. And in this experiment we show that if we have a latent set where the sort of bi-invariant that we use is actually not bi-invariant to any transformation at all, if you transform the latents, so you, for example, you rotate, translate them, you do end up with sort of this distorted reconstructions, which makes sense. So this is exactly why we want to introduce this grounding. In the middle row, we show what happens if you only have translation equivariance. So if you rotate the latents, you're still going to mess up the image. And then below is what happens when you also include these positional or the orientational information, actually, I should say. We show that this way of parameterizing conditional neural fields leads to improved reconstruction performance. So you get higher PSNR, essentially, on the same data sets compared to the original functa framework with a similar number of latent degrees of freedom. And it also works for point cloud data, for example. So in this setting, we're using point clouds and voxels to represent 3D shapes, and there this paradigm also performs. And then what we actually want to use these latents for is some downstream task, right? So if you're operating on the weights of a neural network, so the very first example of neural fields that I said originally, you might, for example, use a graph neural network to classify these weights. If you have a single latent vector, you might use an NLP. And in our case, because we have this latent point cloud, we use an equivariant graph neural network. There's also the downstream task. If we want to retain the equivariance properties, we need to include these constraints in the downstream model as well. We show that this tremendously improves performance on classification of non-aligned data sets. For CIFAR, we're getting an increase of 13%. That's quite, we're quite happy with this. So this essentially to us shows that these inductive biases that we introduced in conditional neural fields really help with downstream performance as well. So this is a nice gimmick experiment that the latents that we now end up with actually have these, they're a set, right? So you can actually operate set operations on these latents. For example, you could take half of the latents for a single image, stitch them together with half of the latents of another image. And this is of course very important research being done at the University of Amsterdam. A bit more serious application is this Umbria data set. It consists of images, satellite images from areas that have flooded. So there's images before and after the flooding, and the task in this setting is essentially to predict or to segment out the area that has been flooded. And we show that even when fully unsupervisedly fitting latents to these initial satellite images, and then training a separate model completely separate from any image data on this downstream task of segmentation, we get pretty good performance. And then one of the nice properties of neural fields is because they're resolution free, you can also do resolution transfer very easily. So you could, for example, train a neural field backbone on a given resolution. In this case, we trained on 128 by 128 images, and then we tested segmentation performance on images of 64 by 64 resolution and 256 by 256. And as you can see, the performance is very similar to this. It stays very constant without any fine-tuning on these tasks. And also, sparse data is not really a problem for neural fields. In this setting, we basically mask out any percentage of the pixels. So this is performance when all of the images are fully observed. If we drop out randomly 50 or even 90% of the pixels, the performance decreases only slightly. And to us, this is really a sign that indeed this neural field is able to sort of recover the underlying continuous structure of the data. Now, nice thing is that, of course, we can also apply this to spherical data. So this is an example of forecasting over a globe. Then more recently, so this is very preliminary work, but more recently we've been very interested in trying to scale these methods up to larger scale data. And through a lot of engineering efforts of our team, we are now managed to actually fit larger scale images also in a single gradient descent step. So we're quite happy with this. Question?
Yeah, I was wondering about this. So how many latents do you have, for example, for such a small image?
So this is a good question. For these images, essentially no compression is happening in the latent space. So what we end up with is a set of 256 latents of size 256. So you're ending up with a very similar number of parameters. But it still has all the nice properties of neural fields. But this is actually one of the limitations that I would touch on a bit later. That ideally you would like your latent space to semantically sort of compress the data, right? And one task that we are now looking into, which also these are very preliminary results, we're quite happy with them, is generative modeling over these latents, so using them actually in a diffusion model as inputs. And we're getting some pretty nice results here, I think. So I have some more nightmare fuel images for you here. There's a couple of limitations. Clearly, as a representation, it's still not perfect. And I think actually one of the main limitations that we have currently is that no real compression is happening. So one of the things that we want to look into next is seeing if we can maybe somehow find a way to compress these latents to make them more information dense. And it would also make it easier probably for downstream models to operate on these latent spaces. And then, of course, these are all applications on images, but I think where neural fields might really sort of shine is on 3D data. This is also very useful often, is representing 3D scenes and stuff, for example. Okay, perfect. Now I'm going to move on to another application of equivariant neural fields, and I might have to go through this quite quickly, but the idea is globally the same. So we just take this equivariant neural field model that we had and we apply it to forecasting. So basically we extend it to the temporal domain. So the idea is you have a ground truth trajectory of a PDE, so in this case the shallow water equations over the sphere, and we would like to be able, given the first state of this PDE, so an initial observation, we would like to be able to forecast the solution for the PDE. And now the nice thing, and the reason why you use neural fields, is because these then give you the possibility to evaluate the solution continuously, so meaning at any location in space, and specifically to our method also any location in time. So we're really looking to build a space-time continuous representation. Yes, question?
So one of the advantages of neural fields is that you could go off the grid, but in this case you have a sphere.
Yeah.
So that means that it's not confined to the sphere unless you're, so I guess my question is, how do you confine it to the sphere?
Yeah, so in practice we use spherical coordinates as input for our neural field. So then, yeah, that sort of solves it. But it's a good question. There have also been approaches, I think Functa, so the original Functa paper, instead uses 3D vectors on the sphere. So yeah, I guess 3D vectors on the sphere as inputs to the neural field, which you do have this problem, and you could in principle also evaluate this I guess off the manifold of the sphere, but it works. No, that works. Yeah, so the idea here is that we learn a set of latents that encodes for the initial state, and then in this latent space of the neural field, we then learn an equivariant neural ODE that's gonna forecast the latents and produce essentially a trajectory through latent space that encodes for the solution in, let's say, pixel space or in real space. So this is what the framework looks like. It's very similar to what I just mentioned. You initialize your latents randomly, and then you optimize them to reconstruct the initial state. You then use a neural ODE, that's here. You then use a latent space neural ODE, an equivariant one, actually, to forecast the trajectory in latent space, and then you can decode this trajectory at any location and time point that you would like to have your solution for. And for that we also just sample the equivariant neural field like I showed before. So very quickly then, to make it a bit more formal, this is the optimization objective we end up with. We're just minimizing the MSE between the reconstruction for a given state and the ground truth for that state, where the latent for a state is given by this trajectory in latent space, which is modeled through this equivariant neural ODE. Makes sense? Any questions on this? Now I'm going to show some pretty images. So these are forecast solutions of our model on the Navier-Stokes equation. In this setting, the model is trained to forecast for 10 time steps. So for, let's say, from the initial state, for the next 10 time steps, you have labeled data. And then we show that it actually also learns to generalize quite decently for a while beyond the training time horizon, although it does deteriorate at some point. And again, we show that neural fields have this nice property that if you have sparsely observed initial states, the whole thing still operates quite well. A lot better than baseline methods that we compare against, classical baseline methods. And it also allows, again, for this decoding at any temporal resolution. So let's say you have, in the training set, you have a resolution of time steps of size 1, let's say. Now you can also evaluate it at a higher resolution time grid. And these are just results to show that, again, it also works for funky geometry. So here we have shallow water equations on the sphere, and these are quite cool. These are internally heated convection equations in a ball. So this is actually a solid ball. And of course, a neural field can also model this as long as you have coordinates and signal values. So we observed that these equivariance properties do help a lot. So the idea is that if these PDEs are indeed equivariant and constraining the whole framework to be equivariant, get you better performance, and indeed it does. And then, yeah, lastly, I guess this sort of line of research relates to research that has also been going on in industry, where Microsoft released earlier this year this AOA model, very large pre-trained climate model. They use actually quite a similar approach. They have an explicit encoder, but their latent space is where they model dynamics is actually sort of geometry grounded, although it doesn't have the nice equivariance properties. And I think with this, I will give it back to Erik for 4 minutes.
Yes, thank you, David, that was really well done. I want to get back, just keep it short, right? And maybe I'll just use this opportunity to talk about Pokemon. So I brought some cards with me. I want to get back to the equivariant deep learning paradigm, and why do I want to talk about Pokemon? Oh, can you turn to it? It's because we've been developing equivariant architectures. And then every time you present a new architecture, you have to come up with acronyms, and we came up with one called Bonita. It's this one, if you look at the camera. It's a fire Pokemon, and super fast, and I'm gonna give some, so it's this paper essentially, David referred to it, and actually if I had the time I would go a bit more about these attributes, these pairwise attributes that we use to condition the neural fields on. We derived them in this paper and generalized them then in the paper that David presented. But primarily what this paper presents is really a practical and fast method for equivariant point graph neural networks. We derived this notion of these attributes that you can use to condition your neural network on, and this insight that convolution is all you need. Sort of like a different perspective on equivariant neural networks that we've seen so far. So with code in the repository, it's the model is called Bonita. It's a position orientation space networks based on invariant attributes. So that's how we came up with this attribute, with this acronym. I just want to quickly go over this as a promotion talk essentially, because we benchmarked this extensively on different type of tasks. One of the highlights is that it's more efficient than many of these tensor field based or Clebsch-Gordon based neural networks. And the idea of our approach behind this is basically that we want to get around this Clebsch-Gordon tensor products, and we did that by adopting this regular group convolution viewpoint, which is sort of like a template matching viewpoint, but that circumvents the need to work with spherical or Fourier-based irreducible representations, but at the cost maybe at some discretization artifacts, which we show do not really matter in practice that much. The benefit is that it's still able to represent directional information, which other invariant methods like EGNN, for example, are not capable of, while still preserving the universal approximation power. Okay, this is Bonita again. So Bonita is a fire Pokemon, and it's super fast, so we thought it was a nice acronym for this method. Basically, for generative modeling, these kind of equivariant methods make a big difference, and we actually saw that not for molecules but also for shape generation in a follow-up paper, because if you want to generate geometry, you want to know how to place a component relative to others, and so these neural networks internally need to be capable of representing directional information. And this is something that this is EGNN based, otherwise the whole generative modeling frame is exactly the same. So we see that EGNN drops heavily in performance relative to this one, and I think we can primarily attribute that due to the fact that our model is capable of representing directional information internally, just like the tensor field type network, but now in a way that is only based on scalar values. Yeah, I just want to move on. Like, we did a lot of benchmarking. I just want to refer to like a talk I gave at the GRASP seminar and the group of Kostas Danielidis. So if you want to learn quickly how we derive these invariant attributes that David also talked about, maybe you can Google for a video of that, because what you're going to see is a lot of slides that I don't have the time to explain. So actually I want to fast forward to maybe the next Pokemon, which is this one, and then I'll conclude after this. So basically we've seen a lot of discussions lately on the utility of equivariant neural networks, whether or not those are really necessary. And it kind of was triggered by this one sentence in the AlphaFold 3 paper that generated structures using neural networks that didn't exploit any equivariance at all. I think there was a kind of a silly sort of hype behind this because the problem doesn't really require invariance, but still it got people thinking, and I think it's very valid to sort of test the hypothesis of the utility of equivariance. So we too started sort of exploring this, did a lot of benchmarking on different tests that require equivariance or does not require equivariance in a follow-up paper. And for that purpose we developed Rapidash, so the evolution of Bonita. And this is basically a scalable version that handles point clouds up to sizes of thousands of points, like ShapeNet, in a kind of UNet, fully equivariant architecture. So this is work led by Shavri, together also with Christian at one of the NeurApps initiators. Basically what we explored was on the spectrum of complexity of tasks, where do equivariant methods really make a difference? And we kind of hypothesized that if you have classification, which is a somewhat simple task, so it's based on recognizing geometry, so maybe that's somewhat easy. Segmentation, that's a task where you have to place labels relative to a geometry. Generation, as said, yeah, you really need to understand what you're generating and how to compose parts relative to each other. So that's considered more challenging. And then you have dynamics forecasting. So we kind of picked tasks on the spectrum of challenges. We did a lot of benchmarking, and so don't have time to go over all of this, but I'm just going to quickly summarize these results into hypotheses. So we formulated some hypotheses, and I'm just showing the results. So one was whether or not equivariant methods are more data efficient. Well, that's obviously is the case. It's a well-known result, but we tested it again in this paper. Second, we do see that the advantage of equivariant methods really depends on task complexity, whether complex tasks benefit more from this equivariant paradigm than simple tasks. Even when the task is not requiring invariance, for example, if you do ShapeNet model shape generation, you can always generate a shape on an axis-aligned setting, but even on those settings, this generative modeling based on equivariance really makes a difference. Hypothesis 3 was basically assuming, okay, what if you just scale up a simple non-equivariant, we could also get such a performance? Well, that doesn't work. So really, this inductive bias makes a difference. Also, equivariant methods are constrained neural networks. So sometimes if you don't need rotation invariance, for example, model net classification, then it might be worthwhile to not make it also rotation invariant and just stick to translation invariance. And also 5, so there's also been trends in literature on symmetry breaking. This is something too that can actually sometimes be beneficial to the task. For example, when you provide XYZ coordinates as input to a neural network, then you kind of break equivariance because you provide input on a global reference frame. But you provide geometric information more explicitly, like here are the coordinates, whereas the convolutions in themselves only leverage geometric information implicitly via pairwise distances and whatnot. And so we show that, well, it can pay off to actually break symmetry in a way while still preserving the internal weight-sharing structure. Yeah, this is the last paper I just want to highlight by Friso de Kruijf on a combination of manifold learning and generative modeling. So I would say just check it out if you're interested in generative modeling. It's called pullback flow matching, where essentially we do generative modeling on the actual data manifold, which we learn via tools from isometry learning. To wrap up, so we've kind of covered the spectrum of geometric deep learning on the equivariant deep learning side, and now I think it evolves towards more geometry-grounded representation learning using the tools that we've developed over the years. There are some inherent limitations, namely the texture bias, which we basically covered via our solution would be via equivariant neural fields to make these representations more explicitly geometric. And finally, I just want to end with some inspiring paintings. This is by Picasso, where you see a gradual abstraction of geometry, but still you capture the essence of the thing into kind of abstract compressed representation, right? And that's something that we hope to achieve also with our methods. And yeah, so this is for Thomas. and the painting that sort of also inspired all of this, that the essence of all of our data, essentially, right? All our real world data is following laws of physics and geometry. So that also the neural networks that handle these data structures should have a notion of, well, computing with geometry, and that's what we're aiming for. And David showed extensively that we finally make progress in inferring geometry grounded representations. So yeah, with that, thank you for your attention. So, anyone want to talk Pokemon? Okay. All right, team.
Technical questions or?
I know, it's
I think so. I don't think we're on.
Thank you very much, Erik. We are happy to take questions both locally and online from this moment, so feel free to ask questions there as well. Thank you.
Okay, so I was wondering, is that meta learning process, is it also equivariant? So if you were to initialize the whole data set, fit, get latents, and compare them, would they be?
That's a very good question. I think in the limit, yes, because well, it sort of depends on how you implement this initialization for the poses of the latents. But for example, if you sample them randomly from a Gaussian distribution over your manifold, then yeah, rotation applied to this Gaussian is going to end up giving you the same distribution. So I think in the limit it should be, but in practice we try to initialize the latents sort of uniformly over the data manifold. So then no, it's not going to give you exact equivariance, because yeah, if you rotate your image or you shift your image, then now suddenly you have latents where you didn't have latents before, and they're going to be optimized to reconstruct this unseen part of the image, basically. Yeah, that's a very good.
so the gradient operator is equivariant, right? So the one that you use for gradient descent. So that part is equivariant. It's just the initialization. Yeah.
Yes.
So one of the advantages of neural fields, you also mentioned it, is that we have they scale with the signal complexity, right?
Yeah.
Not with the resolution. Do we lose that with locality?
That's a good question. I think in this current form, what we see, we do lose that, I think, because, well, the results that I showed you for ImageNet just now, there's no real compression happening. And if you, for example, use a VQV as an autoencoder trained on ImageNet, the latent space there is a lot smaller. So in terms of information density, this is definitely not the most or the best.
Also, you mentioned the ball experiment, right? Which is a 3D dense point. Do you have a very dense set of latents?
Okay. No, there, in that specific case, there's a pretty big reduction, I think. Top of my head, we have 36 latents of size 16 for a grid of size 46 or 64 by 48 by 32. So the latent space is gonna be a lot smaller, I think, than the signal. But I think there's just a lot of redundancy in the signal, like a lot of local correlation. But we do see that for more complex PDEs, so for example, for the shallow water equation versus the Navier-Stokes that we did, Navier-Stokes was quite simple. We do need a bigger latent space, so it does scale with complexity. Yes.
So getting back to the question from earlier with the reflection symmetries, how will that work?
Okay, yeah, so I guess you would have to design a bi-invariant to reflections, and I don't know, maybe Erik has this slide.
No, yeah, it's really that. So if you have the group of translations, rotations, and reflections, then you need to make sure that the point cloud has an action on it defined. And right, 2D point clouds, you can reflect them. So that's a valid representation space. And then you need to compute invariance, like what if I reflect my latent point and my pixel coordinates, what is the attribute that stays invariant? And one of them would be, for example, the pairwise distance. So the distance is an invariant under reflections. If you want to gain expressivity, for example, we augmented the latent space not just with position, but also orientations. But now you could consider maybe also adding a parity term, right? That sort of says, okay, what if I flip the image? What would the patch look like? So that's, and then you would sort of get a richer set of invariants that parameterize the neural fields.
So to follow up on that, do you think that because you were training it with gradient descent, would the fact that it's a very discrete group, so reflection,
Yeah. Yeah, that's
really have that much gradient information on that, would that cause trouble?
Yeah, that does cause trouble, I think, because yeah, that requires maybe with some Gumbel annealing you get out of this. But yeah, our current approach to inference would be gradient descent based. Yeah, and then you need to take care of this. Yeah.
So there's a few more questions online. Is the meta-learning optimization to obtain the latents also equivariant? I think you've already answered this.
Yeah, so,
And then there's another question. What are your thoughts about using this approach for large language models or language models in general, where you don't have any apparent symmetries?
Yeah, I would love to explore that. I don't have experience with this, but conceptually I would think that the language model should also have a geometric internal representation, right? So my vision would be to, instead of working with tokens of vectors, you would work with tokens of latent point clouds, right? And then a bit like AlphaFold 2 had this iterative equivariant point or invariant point attention module, which basically also represented a sequence of amino acids with some decoding step, like decoding the current vector to a point cloud and then matching that point cloud with another point. And I think that's beautiful. It's like it uses internally some geometric representation, and yeah, that will be my vision on this. I don't have the resources or the the expertise to actually work on that. But if anyone has, I would love to collaborate.
Just a quick question. So initially you said you were using transforms for images, and then you had this like Gaussian masking to kind of normalize stuff.
yes.
Why not just use Bonita there automatically, since it's like includes these localities by default, like kind of being conditional on distances and stuff?
Yeah, because there, if you let, so Bonita essentially uses let's say a small neural network to parameterize the message passing function, right? And you're saying why not directly input the relative distance into this message passing function? Well, because then you still, this message passing function still has the freedom to learn, let's say, larger activations for further distances, right? There's nothing necessarily constraining it to give higher output values, let's say, for points closer, right?
So on the intuition part of Erik's part, you mentioned the Sora model, right? And then you have all these disturbances in cadence, generation, all of that. So then you kind of reason the necessity of geometric ground representation, and then you show the images generated by your method with like distorted dogs. So my question is, what do you think is your approach lacking at this point at scale, which would be funny, or is it something else that is needed?
So I think so. First of all, we showed that these representations do contain geometric content and are sort of more information rich, where when you compare to just fitting one vector representation to it. We have these equivariance properties in all, and we show that we can do classification, segmentation, and even PDE forecasting entirely in latent space. So that sort of establishes, okay, these latents have some geometric meaning. But now when it comes to generation, we now got this to work, but we still generate maybe dogs with 5 or 6 legs or something, right? And so this is something that we now are going to focus on too, like how can we leverage this geometric structure to also make sensible generations. And this is in a way in a very early phase that we're in, that we're just exploring the generative modes too.
I personally think it's really this notion of compression that's sort of missing. The latents themselves are very, I guess, not very information dense right now. So to give a bit more context, these weird-looking images that we generated were generated by training a diffusion transformer on equivariant neural field latents. The original diffusion transformer paper operates on the latent space of a VQVE, which I think is 4-dimensional, whereas our latent space is 256-dimensional. So I think the biggest problem is that because our latent space is so big, essentially, it just complicates downstream tasks a lot. So now we're thinking of ways of addressing this, and I think this is really the main problem. So we want a denser representation and maybe fewer latents, or maybe we've been discussing with Chase also about maybe a hierarchical approach to parameterizing the latent point cloud.
I want to stress that, so we've been working on generative models for shapes and for point clouds or for molecules, so we got that part covered separately, but now this is a different story where we also have essentially have a latent variable model, so we don't know what is the latent point clouds. And currently it seems that our inference method is emphasizing more on the textual patterns still, and not so much updating the position information. So there's still a lot of room to gain in sort of gauging this inference model based on geometric priors and shape variations. And yeah, so that's on our to-do list.
So one last question online. Whenever you learned the PDEs, did you notice anything, or did you look into the dynamics that were learned and whether they behaved physically?
No, we didn't really. But it would be very interesting, I think, to see what actually happens in the latents. But I think in practice we did inspect the sort of distribution of the positions or the poses that the latents that were fit to specific states had, and there it didn't really give us very it doesn't necessarily give you very sort of semantically meaningful poses for the latent. So it's not like there's a latent at every vortex or something like that. It seems that the model still is able to sort of learn to represent patches of this signal regardless of sort of the pose. So this is another thing that actually we think we should explore. I think this is mainly due, not going into too much detail, mainly due to the reason that we're using SGD to optimize both the latent vector and their position. And so you're sort of optimizing two objectives. You're optimizing the MSE and optimizing the gradient with respect to the position, but then also with respect to the latent itself. And well, intuitively, as soon as you did a single gradient descent update, now this latent encodes for a local patch. So it doesn't make sense to move this patch anymore, right? So we need to find a way to sort of update them, I guess, simultaneously or more, like a more integral approach. This is also a thing that we're thinking about. Yeah. One question. Yes?
My question is about the PDE forecasting. So once your model is trained, then you can evaluate the PDE solution between data points, basically.
Yeah.
And I think for sure the model is not just linearly interpolating between the data points. Do you have any intuition or any grasp on the sort of implicit bias of the interpolation that your model exerts on the signal?
Yeah, so I think it's a very good question, and there's been a lot of research in neural fields literature, and also I guess like neural network optimization in general. It shows that neural networks have a tendency to model lower frequencies first, let's say, and so for these neural fields you actually usually use some way to address this problem. But to answer your question more specifically, I think what you might see is that it sort of tends to a smooth, like a maybe overly smooth sort of interpolation.
So is this true for all neural fields, or do you think that very neural fields have a difference there?
I think this is true in general for neural fields, and one of the most well-known architectures it's called Siren, and it's just an MLP that uses sign activations. And really, the reason it uses sign activations is to introduce these higher frequencies, I guess, back into the model. And we ended up using an RFF, so random free feature embedding. But I think this happens to neural fields in general. I don't think very neural fields necessarily is specific. Okay.
Yeah, okay. Thanks everyone.
Yeah, thanks. Thanks for
Thank you. Thanks a lot, Erik and David.
Thank you.
Yeah, you're welcome, and thanks for inviting us.
I mean, that was great. The community is super vibrant, and we're very happy, of course, of how is it going and of your talk as well. I actually had a question which can be sound more of a perspective. I mean, so maybe I can ask it now. Erik, you started your presentation with some videos, right? I guess they're coming from some video diffusion models or something like that, where you show the inconsistency evolving through time. And I was wondering whether there's, I mean, you can close the loop and go back to that in some way. Do you see a gap between I mean, most of the models you've been talking about are for images, and besides the equivariant PDEs, of course, but that's a different problems because you have dynamics, which is underlying the.
Yeah.
There's a lot of noise. Okay, so I was wondering whether, I mean, the gap between going from images to videos can be simply like reduced by imposing some, I don't know, like Galilean, some sort of group structure that acts through spatial temporal.
Yeah, in a way, I think generating videos with this concept would be actually generating neural ODEs, I think. Yeah, you fit an initial state, the initial frame, and then just like with the PDEs, the evolution of this video is actually also represented by an evolution of these point clouds, which we now did with the PDE forecasting with neural ODEs. And yeah, I think this will be super challenging, but also super interesting, right? To really treat videos as neural ODEs. And yeah, I'm not sure if there must be some papers or literature on this, but I don't know.
I haven't seen a lot, but this is of course very interesting for neuroscience as well, because the way now we predict the future states from.
Yeah, and so what we want to explore actually is this probabilistic modeling and this posterior inference approach, right? We also have these models of perception and dynamic perception, and that would be really cool to integrate these things together.
Yeah, totally. Okay. Thanks a lot. I hope to see you at NeurIPS as well if you're around in Vancouver.
Yeah, unfortunately, I won't be able to go to NeurIPS, but I hope to meet you sometime soon, maybe here in Europe, somewhere closer by.
Yeah, that would be great. Thanks a lot, and thanks David also, and Chase, of course.
All right, thank you.
Bye. Have a nice day. See you.